Okay, welcome everyone. Welcome to lecture 3. Today we're going to look at a couple of applied uses of differentiation that are a little bit different to how we've done it before. They have their own specific uses. Well, we'll see when we get brought into it. So the first one we're going to look at is a thing called implicit differentiation. Now you find this stuff in the notes, obviously. So implicit differentiation is all about when we have an equation which tells us something about x, say, and y at the same time without stating one of them explicitly in terms of the other. So for example, what we might call an explicit equation might be something like y is equal to mx plus c, or y is equal to x squared plus 4x plus 3, or y is equal to sin x. In other words, all the y's on one side, all the x's are on the other. And in fact, the y's to single power. So it's something like y equals, or it could be x equals y squared plus y blah blah blah. Let's do that. X equals cos squared t plus t. R equals e to the power t minus t squared. All this kind of stuff. All that's important here is that they've got something equal to another variable, a function of another variable on the other side, and there's no mixing of stuff. An implicit equation doesn't give you that kind of advantage. So that's an advantage because that means if I want to work out y for any point, x, I just stick x in all these places on this side and it would give me it. Implicit equations are things like the equation of the circle, which we have looked at before, so something like x squared plus y squared plus plus 5 5x minus 6x equals 10, something like that. So here we don't have an equation which tells us what y is directly in terms of x, and in fact in a lot of cases it's not possible to give us directly an equation that gives us y in terms of x. There's always going to be this mix. This is the best we can do. And so the question is then, well, how do we find the derivative of this thing? How do we find a function which tells us the gradient of the thing at any point? Because if this, I'm not going to draw it. I can't bother try to work out what circle that would be. But let's just say this is some generic circle, like that should be a y actually. Let's say this is some generic circle. I think it would be back here actually. Something like that. Now this thing should still have a gradient at every point, right? If I point there I can see a line, if I can see a line I can see a gradient. So why can't I find an equation which tells what that gradient is? Well, you can, it's just obviously not going to be as simple as saying, well, if y equals mx plus c, then dy by dx equals so on and so forth. We're going to have to come up with a new method. So let's say something. We're going to use the chain rule a bit, sort of implicitly here. So implicit differentiation assumes there is a form. Assumes there is a form where y is a function of x and only of x. It assumes that exists, but it never ever has to know what it is. It doesn't have to know what it is at all. It just has to make the assumption that it exists. So we need a couple of extra things here. If we've got, so I'm going to introduce this notation. I don't know if I've used this before, but d by dx. So d by dx just means differentiate the next thing. So if I do d by dx of f of x, it's just df of x by dx, right? I'm just differentiating this equation in terms of x. That's everything we've done so far. But what we might have to do is do d by dx of, I'll put this in brackets as well, of a function of y. So some equation that's written only in terms of y, we're going to try and differentiate with respect to x. Well, using the chain rule, we know that that's going to be equal to d by dy f of y times dy by dx. And now this is key, because this means that any time we want to try and differentiate a term that might appear in this kind of equation, so say we're trying to differentiate y squared, this means that instead of trying to differentiate with respect to x directly, we differentiate with respect to y and multiply it by dy by dx, and we literally just multiply it by that symbol dy by dx. Because the goal here is going to be to get an equation out that has a bunch of these dy by dx's in it, and then rearrange it so that dy by dx is a subject. So it's going to be dy by dx equals blah. So let's have a go at that. So let's look at this thing. So if I've got x squared plus y squared plus 5x minus 6y minus 10 equals 0, then that means if I differentiate the left hand side, I should get the same as what I get if I differentiate the right hand side. So then if I differentiate x squared, I get 2x. Easy. Then if I differentiate y squared with respect to x, then let's use this rule. So differentiate with respect to y first, so that's going to be plus 2y, and multiply it by dy by dx. Okay, so let's just leave that there. Plus 5x differentiated with respect to x is this 5. Minus, okay, 6y differentiated with respect to x, it's going to be 6y differentiated with respect to y, then times dy by dx. So differentiate minus 6y with respect to y is going to be minus 6. And then multiply by dy by dx. A bit of time sign in there. Oops. Minus 10 differentiated with respect to x is 0. And then 0 differentiated with respect to x is 0. So that's going to be equals 0. Now I've done something I was actually afraid of that I probably should have kept track of, but I've run out of space, so let's just move this up a little bit so I can keep going. So you can see that's just going to stay there. So we've got 2x, oh, come on you bugger, 2x plus 2y dy by dx plus 5, plus 5 minus 6 dy by dx equals 0. Let's move everything with a dy by dx attached to one side. So we've got 2x plus 5 is equal to 6 dy by dx minus 2y dy by dx. And then dy by dx is a common factor, so we can actually take this out. So 2x plus 5 equals dy by dx. So dividing everything by dy by dx, you get 6 minus 2y. And then to finally get dy by dx as a subject, we're going to take this whole thing and divide by that on the other side. So 2x plus 5 over 6 minus 2y is equal to dy by dx. So we've found a function which gives us the gradient. We've found something that tells us what the gradient of this function is at any point, but it takes both x and y as its arguments. We have to know both points on that line. So for any point on this circle we drew earlier, if I want to know the gradient at this point here, say I need to know both the x and the y coordinates to do so, but it's perfectly able for me to do that. Okay, I'll do another one. I'll do a more complicated one. Let's do x squared plus x squared y minus sin y equals x cos y. So actually a horrible one. Okay. So these terms here are new and will be very annoying, because not only are we going to have to do our little trick where we differentiate with respect to y, then differentiate with respect to x, but we're also going to have to use the product rule, because the idea is that x squared is a function of x, and we've said that in implicit differentiation y is a function of x as well. So let's differentiate this. So this becomes 2x plus, and remember we do our f, g and f dash, g dash stuff. So f here is x squared, g is y. It's confusing because my g's look like y's as well, but bear with me. So f dash g is going to be, well, x squared differentiated is 2x, so it's going to be 2x y plus fg dash. So y differentiated with respect to x is going to be that differentiated with respect to y times dy by dx. So it's going to be plus x squared, y differentiated with respect to y is going to become 1 times dy by dx is dy by dx minus, and then again we we differentiate with respect to y and then multiply it by dy by dx, so minus sin y becomes cos y when differentiated with respect to y, and then we multiply it by dy by dx equals, and again we're going to have an fg thing here. So f dash g, remember it's this equation here, fg dash, the whole of fg dash is equal to f dash g plus fg dash. So f dash is going to be x differentiated, so that's 1 times cos y plus, and then fg dash is going to be x times that differentiated with respect to x, which is going to be that differentiated with respect to y times dy by dx. So oops, did a big long smear there, plus, so f is just x, that differentiated with respect to y is going to be minus sin y times dy by dx. Tidy this up, 2x plus 2xy plus x squared dy by dx minus cos y dy by dx is equal to cos y minus x sin y dy by dx. Okay, so let's just tidy everything up. Now we want to move everything that's got a dy by dx attached to it on one side, or like maybe even, yeah, we'll keep this stuff here and move this other stuff across. So we're going to have x squared dy by dx minus cos y dy by dx, and then this is going to move across, so it will become positive, plus x sin y dy by dx is equal to, so that cos y is left where it is, but everything without a dy by dx here is going to get moved across, so minus 2x minus 2xy. 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. Good. Okay, so now everything here has been multiplied by dy by dx, so we can take out dy by dx as a common factor. So dy by dx, x squared minus cos y plus x sin y is equal to cos y minus 2x minus 2xy, and then this can come down to divide, so dy by dx is equal to cos y minus 2x minus 2xy over x squared minus cos y plus x sin y. Just dodging the tail of my y here. So we've got an equation for dy by dx. Okay, so we differentiate everything with respect to x, but whenever there's a y involved, we have to differentiate that term with respect to y and then multiply by dy by dx. And then any of these things that seem like multiplications of two functions, we have to use the product rule, which is this thing here. So let's do one where we actually have to find the gradient. Okay, so let's do find the gradient of the tangent to the circle with equation x minus 3 squared plus y minus 2 squared equals root 13 at 0.55. Okay, so the trick with these things is that when I'm making up these questions, I have to make sure that this point actually exists on this circle, because obviously I could pick any numbers here, but those numbers won't necessarily lie on the circle here. I would still get a value for the gradient if I put them in, but that value would be absolutely meaningless. Okay, so let's have a think. So let's split these out. We're going to get x squared minus 6x plus 9 plus y squared minus 4y plus 4 equals root 13. So x squared minus 6x plus y squared minus 4y plus 9 plus 4 is 13. So this is funny, minus root 13 equals 0. Okay, so let's differentiate this thing. So x squared differentiated is 2x, minus 6x differentiated is minus 6. 2y, y squared differentiated is going to be 2y times dy by dx. So the trick with these ones is you simply just differentiate them as if they're with respect to y, and you just slap dy by dx in the front. It's actually less complicated than it looks. Minus 4 dy by dx. Oops, I forgot to write the dy by dx after saying that. Ugh. Right. That becomes 2x minus 6 plus 2y dy by dx minus 4 dy by dx, and then all this is going to disappear, and that differentiation is going to be equal to 0 as well. So this equals 0. So then move this stuff across and leave this stuff here. 2y dy by dx minus 4 dy by dx is equal to, that becomes positive 6, that becomes minus 2x. So 2y minus 4, so I'm taking out dy by dx as a common factor, is equal to 6 minus 2x, and then I'll use this line here, and that implies that dy by dx is equal to 6 minus 2x over 2y minus 4. So that's us got our equation for the gradient of the circle. Let's now find the actual value of the gradient as we've been asked here at the point 5, 5. So x equals 5, y equals 5. That implies that dy by dx is going to be, just plug these numbers in, so 6 minus 2 times 5 over 2 times 5 minus 4. So that's 6 minus 10 over 10 minus 4. So that's going to be minus 4 over 6. So that's minus 2 over 3. And that's our solution. So we've got a circle, we've found the gradient of the circle at the particular point 5, 5. That's equal to negative 2/3. So there's an extra kind of trick to get your head around. There's questions in the notes for you to try out. But a whole extra trick to work out here, and it does unfortunately incorporate some of that product rule stuff that we did recently. So let's move on to parametric differentiation. Parametric is another kind of mixed take on differentiation, except instead of the mix being between x's and y's, it's more like it's a third variable that's been put in the mix. So that was a good line. So parametric differentiation refers to like functions of x and y that have both are based on a third variable. So for instance, if you think of I'm going to do a circle again. Let's see if I can draw a nice circle. Yeah, that's good enough. Say we've got a ball that sits in a circle. Let's say it's the edge of say it's a planet orbiting a sun. Right? This thing's moving around with time. So it's got some velocity v that it moves around with. What we find that this circle actually has its position of this planet can be described by equations of the sort that x is equal to cos t and y is equal to sin t. Okay, so as long as the things inside the brackets here are the same essentially, so I could do cos 4t and sin 4t or cos anything t to get the right numbers, and there could be size in front of this, so like the size of this radius here. We'll call this length 1 though. Let's say we've changed the units to make sure that's 1 unit of whatever it is, that's 1 orbit worth. Then as time moves on, these functions together will perfectly describe where that thing's position is at any particular time. So for instance, at time 0, that's going to say that x is cos 0, which means it's on this line somewhere. Sorry, cos of 0 is 1, sorry, so x is going to be in here. And y is going to be sin 0, which is 0, so it's going to be here. So it's going to be y is 0, x is 1, so it's going to be sat here. Then as time moves on, you'll find that it creeps round. So let's say it's 90 degrees. So cos of 90 is going to be 0, so x is going to be here, and sine of 90 is going to... Oh, actually I've got this going the wrong direction. It'd actually be going in this direction. So maybe we'll write that out and do that instead. So we're moving in that direction instead. And these equations together would describe this thing moving round. So they're parametric equations in that they're not based directly on each other, but on a third parameter, and they both exist in the same system as well. What we're going to do is look at how we differentiate these things and how we get them to interact, and things we can talk about. So first thing to talk about is the velocity. Well, so for parametric differentiation, we usually talk about it being in terms of t, in terms of time, things that two coordinates that change together in terms of time. So we tend to be differentiating with respect to time all the time, or at least it's worth calling t the parameter. So, what's notation? Shorthand for dx by dt would be x with a dot above it, and similarly dy by dt would be y dot. So it's just shorthand. It's going to come in useful in a little bit. So whenever you see a symbol with a dot above it, it usually means someone's differentiated that with respect to time. So for any parametric system, we can talk about the velocity of the system being equal to the square root of x dot squared plus y dot squared. So if you like, it's the hypotenuse of the triangle. It's saying that once you've worked out x dot and y dot, find these are the components of a velocity, if you like, acting in different directions. Find what their combined action is. So let's draw that out. Really, we're talking about vectors here in disguise. And that saying would be v. Another thing we can talk about, let's go straight for it, might as well do both these at the same time, is we can actually manipulate this to tell us what the gradient, the linear gradient that we've worked out before is, so that the actual tangent of the object at any particular time. So if we look at dy by dx, which would be the gradient, that's going to be, if I do a chain rule in reverse, I'm going to cheat here. I'm going to say that that's the same as dy by dx, oops, times dt by dt, right? So that's 1 in disguise. Dt over dt would be 1, so I can do that. And then we're going to mash these together, so that would be dy by dt times dt by dx. Which is equal to dy by dt times, well, this is actually, I've flipped that round, so that's dx by dt to the minus 1. So that's equal to y dot, remember from this notation up here, y dot times x dot to the minus 1, or simply y dot over x dot. So let me write that again in summary. dy by dx, the actual gradient of this line, this object's tracing out, that if you were to direct a straight line through it and predict where it to go, is equal to y dot over x dot. That's still not convincing, is it? Y dot over, just so you can see the dots. Okay, so these are the two things we should be able to do with any parametric equation. Find its velocity by finding the two components, x dot and y dot, and then finding its gradient by dividing y dot and x dot. So for any question that might break down, that all we do is we find x dot, find y dot, stick our values for t in, and then put them in these two equations. Put it in that equation first to find the velocity, then put it in this equation to find the gradient. Okay, let's try an example. An object's movement can be described by the equations x is equal to t squared plus sine pi t and y is equal to cos pi t minus t, something like that. Find the velocity and gradient of the tangent to the trajectory of the object when, let's say, t is equal to 10 seconds. Or 10, let's just say 10. Second, the units aren't so important here. T is equal to 10. Okay, so all we do is we say, well, x dot is going to be this differentiated with respect to time. So it's going to be 2t plus differentiate this with respect to time, we get pi cos pi t. Y dot is going to be equal to, so this differentiated with respect to time, cos becomes minus sine, so minus pi sine pi t, because that factor of pi comes out, minus 1. So x dot at 10 is going to be 2 times 10 plus pi cos 10 pi. So you can stick that in your calculator, but that's going to be 20, and that's going to be pi, so it's 20 plus pi, because we know that every 2 pi cos becomes 1 again, so that's a multiple of 2 pi, so therefore it must be a 1, so 20 plus, so 1 times pi is pi, 20 plus pi, so y dot at 10 is going to be, oh, no, wait a minute, no, yeah, I'm fine, so y dot is going to be minus pi sine 10 pi minus 1. So sine at 2 pi, sine is equal to 0, so 5 times 2 pi is going to be 0 as well, so we've got this term just disappears, and we're left with a minus 1. Okay, so we've got the two values, so v is going to be equal to the square root of x dot squared plus y dot squared, which is going to be the square root of 20 plus pi squared plus minus 1 squared, which is equal to, and for as one of the rare times, I'm going to pull up my calculator. There it is. So let's see, that's going to be 20 plus shift pi equals squared plus, and then minus 1 squared obviously is going to be 1, so plus 1. Square root answer is going to be 23.16, which you'll find is probably pretty close to 20 plus pi. So I'm getting away with doing a decimal approximation here in maths, because this velocity thing is a very engineering thing you want to get anyway. So we're just going to call it 23.16 to 22 dp. So if anyone wants a better answer, they can do that to more decimal places. dy by dx is going to be equal to y dot over x dot, which is equal to minus 1 divided by 20 plus pi, which you could kind of leave there. You can't get much simpler than that without having to cheat. Okay. So that's basically all we can be asked when it comes to parametric differentiation. So I will put another quiz up for these two subjects once this is cleared, and we'll see how we get on from there. Okay, so I'll talk to you guys later. Bye now.